So when you're stating this principle, you have to say it like you're telling someone else, like you're looking at. Okay, so this is how we answer this one. All right, so the principle of superposition, right, states that when two or more waves meet or overlap at a point, the resultant displacement is the sum of the individual waves. Right, I know people would argue and talk about whether it's the, like, yeah, if you come to this point on the sum part, is it the vector sum or the algebraic sum? Right, it's not really necessary to highlight these two. Okay, but what we have to understand, the fact that we're talking about displacement, all right, the fact that we're talking about displacement, we know displacement is a vector quantity, so it's not really necessary for you to come here and state that this is a vector sum or the algebraic sum of the individual waves. No, sorry, not really the waves there, individual displacements. Okay, I think it would be ideal to write individual displacement than to say individual waves. Right, individual displacement. All right, so when you're stating the principle of superposition, you have to highlight that we have two or more waves that are meeting at a point, right, maybe in a plane. Right, so these waves can either overlap or they may not overlap, but we're assuming that these waves, as they meet, they do overlap. At that particular point, if you try to find the resultant amplitude or the resultant displacement, normally the displacement is associated with the amplitude, by the way. All right, because you're looking at waves like this. Okay, then you have another one which is coming probably in the same plane or in the opposite direction. It doesn't matter how these waves are traveling. So if they are to meet at a point, like for instance, if I have another one that's probably coming in the same manner, right, like that. So if I'm to find that resultant displacement, it's just a matter of addition. All right, you are adding those two amplitudes, those two displacements at that particular point. Right, so it's not really important to highlight this at this point, but here we're just answering this question, right? So you're just stating what the principle of superposition says. It's not necessary for you to highlight that it's a vector sum or algebraic sum, because already the fact that you're talking of displacement is a vector quantity. So what's the point of highlighting the vector or the algebraic sum? So just highlight that we have two or more waves that are meeting at a point, and when they do meet at that particular point, the resultant displacement is just the sum of the individual displacements of those waves. All right, okay, this is probably how you can answer this type of a question, right? Now let's move on to the second part. All right, coherent light is incident normally. I'm sure you're familiar with the term coherent. This question is mainly on interference, right? Remember, we have two types of interference, destructive and constructive interference. And the term coherent, we're talking about a constant phase difference and the same frequency there, right? Constant phase difference. So for us to have a proper interference pattern, we must have coherent light sources, okay, or coherent sources of the waves. So we have coherent light is incident normally on two identical slits, X and Y. The diffracted light emerging from the slits superposes to produce an interference pattern on a screen positioned at a distance of 1.9 meters from the slit. Fig 4.1 shows the arrangement the arrangement and the central part of the interference pattern of the bright and the dark fringes formed on the screen. Right, this is the diagram. Right, what are we having down there? The separation of the slits is 0.65 millimeters. The distance between the centers of adjacent bright fringes is 1.7 millimeters. Calculate the wavelength of this light. Okay, there's a formula that we can use to determine the wavelength. I hope you remember that formula. Okay, so this is the formula that we use to deal with this type of equation. Right. Just a second, let me change my that's how it's blue. Okay, so what does the formula say? Or maybe we can just highlight the things that we have, the quantities that we given on this question first. All right, so first of all we have A. Remember, A is the slit separation, which is 0.65 times 10 to the power minus 3 meters. It's good to change this using prefixes. And then we have adjacent fringes are separated by a distance of 1.7. So this is X, the distance separation between the adjacent bright fringes, which is 1.7 times 10 to the power negative 3 meters again. And then we have this capital letter D on the screen. If you check there, the distance between the slits and the screen, that's 1.9 meters. 1.9 meters, right? And the question wants us to find lambda. We don't know lambda, so what formula do we use here? The formula that we use, we are going to use this formula, right? Lambda is equal to AX over D. I hope you're familiar with this formula. Normally when we are writing this formula, it comes from X over lambda is equal to D over A, or the other way around. X over lambda is equal to D over A. That's how we write this formula in general. So if we substitute these values, I think we have 0.65 times 10 to the negative 3. Right, multiplying 1.7 times 10 to the negative 3 again. Right, all this divided by 1.9. This is equal to, it's just a matter of using the calculator there. Right, I have 0.65 times 10 to the power minus 3. Right, this is multiplied by 1.7 times 10 to the power minus 3 as well. All right, then all over 1.9 equals, right, I'm getting 5.81578 9474 times 10 to the power minus 7. Right, if we look around, most of our raw data values, if you check, there to two significant figures, so we can actually write this value as 5.8 times 10 to the power minus 7 meters. That's what we're going to have down there. Right, so this is how we answer this type of equation. So your lambda is 5.8 times 10 to the power minus 7. All right, the unit is already there, that's meters. So it's, what was key was to remember the formula there. There's so many questions which look like this, so this is the formula that we use. All right, I know there's the other one where we use a sine theta is equal to lambda x, n lambda, d sine theta. Some they say d sine theta is equal to n lambda. Right, normally we use this one if you are given probably the angle or mostly in diffraction grating, not in interference. Yeah, it's okay to use it here, it's still fine, but that's if you are given all the parameters. But in most cases we use this lambda is equal to ax over d. This one is usually used when you're dealing with the diffraction grating. diffraction, grating.